Hey everyone, it's Mr. Thrasher. I hope you're doing well. In this video, I wanted to go over that Wave Basics assignment. Mostly because as I was going through and checking scores, I saw some common mistakes, some common misconceptions. And it's tough because oftentimes if we were in class, we'd be either working or talking about the solutions as a whole group, or of course, while you were doing the homework, I'd be walking around and clarifying things. And we haven't been able to do that. Quick reminder, you can always email me questions. For this video, I'm just going to go 1 through 7. I won't necessarily do this for every homework, but maybe especially like as we're entering this new unit, they might be a little more common. Feel free to skip as you see fit. Some of you on Canvas might see the note or the comment that says perfect for your homework, and that means, you're pretty much all right. Maybe you don't have to watch this. Everyone else, you will see the questions that are marked wrong. Feel free to skip ahead or watch this whole video as you see fit. Okay, I have a meme that's kind of matching our scenario. There was a bad word in it, so I had to clean it up a little bit. But let's just jump into these problems. We're going to go one at a time. Okay, problem 1. It says you're standing at the edge of the dock. Imagine you go to, I don't know, Half Moon Bay or something, and you're on the dock and you're just watching water waves pass by. And I don't know why you would necessarily do this, but in a span of 5 seconds, you count 3 ocean waves pass you by. It's asking 2 questions. A is asking what is the frequency. Remember, frequency is the number of usually waves, but frankly, it's the number of cycles, the number of items happening per unit of time or per second. For example, in this case, we see 3 things, 3 ocean waves pass. That's the number. And how many seconds did it take those 3 ocean waves? That's 5. Oh, this is how we'd figure out the frequency. The number of waves, or, later on, number of vibrations, the number of wigglings, the number of cycles, okay, per unit of time. So 3 waves in 5 seconds, you put that in your calculator, you get 0.6. And that's per second, or that's hertz. So that's the answer for 1A. Okay, you take the number of waves or the number of vibrations, the number of cycles, divide that by the time for that number. That gives you the frequency. It took each wave, or there was 1 wave every 0.6, or 3 waves every 5 seconds, or 1 wave every 0.6 seconds. That's another way you could read it. Okay. Now it's asking here for the period. That's t. Remember, period has this uppercase t. It's a time, but it's a special time, and it's 1 divided by the frequency. And I just found the frequency above, so that'd be 1 divided by 0.6. You take your calculator, you punch that in, you get about, what, 1 2/3. Okay, or about 1.67 seconds. That's the time it took each wave. 3 waves in 5 seconds, or every wave took about 1.67 seconds. That's problem 1. Problem number 2. Okay, I actually already made the diagrams. I'm going to delete some black boxes in a second, but we're practicing drawing waves, and on these diagrams, it's okay if you hit pause. I wanted to show that there are several ways to draw these diagrams, okay? So here's letter A. Letter A, I want 1 wavelength. There's a couple different ways. So here's like my axes. That's how I drew this here. I took this picture a couple years ago. I could go from right here as I'm about to go up to 1 wave is the next time I'm about to go up. So right here, this is one example of 1 wavelength. But there are several ways you could do it. I recommend you go crest to crest, and that's kind of what I have here in this second example. You start at a crest, you drop down, go into a valley, go back up to another crest. So this is also 1 wavelength. But both of these are correct, and to be honest, there's many ways you could draw 1 wavelength. Here's another one where I'm starting on this equilibrium line and I'm going down. There's a valley, there's a crest. All 3 of these are 1 wavelength. If you drew either of these, you're correct. And to be honest, you could have drawn something that wasn't one of these 3 and still would have gotten it right. For B, 2 wavelengths. Well, if I'm starting here, start at a crest. Here's another crest 1, another crest 2. Here is 2 wavelengths. Again, I could, if I'm looking at my equilibrium line, I could start here and go a hill and a valley. There's one. Hill and a valley, there's two. So again, a couple different ways you could draw two wavelengths. For C, it's 2.5. Again, I don't know if I have to read these out all over, but just know there's many ways you could draw them. For example, here's my hill and valley 1, hill and valley 2, and then I need one more. I need half of a wavelength, because for this one, it's 2.5, 2.5. Here's my extra half. Okay, a valley, that's a half. A hill, that's a half. So together, that's one wavelength. So I also have these extra little crests. Okay, if you went crest to crest, again, you go crest to crest 1, crest to crest 2. This one's a little weird. The crest to the trough, that's also half of a wavelength. So this could work as well. And then D, 3 and, oh man, 3 1/4. So if a hill is half, half of a hill is a quarter. So if I think of it like this, let's see. Here's 1/4 of a wave. Here's another quarter of a wave. Here's another quarter and another quarter. D is definitely tough. Okay, parsing this out in quarters, is a little difficult. But that's number 2. Let's keep going. Number 4, it's funny, when you send out these assignments at these online versions of school, I forget, like in class, we all would be holding tuning forks and we get a sense for them. Some people, frankly, you might not know what a tuning fork is. Maybe that's just a small number of you, but this is a tuning fork. It's something that you hit it and those two little, they're called tines. It's like a leg, here's a leg, here's a leg. They start vibrating. And they vibrate at very specific frequencies. You use this if you're trying to like tune a piano or tune a musical instrument. They're nice because they play one specific musical note, say middle C, for example. Okay, it says that this tuning fork produces a frequency of 256 hertz. Okay, and then it has some questions. Let's go through the questions. A, how many times does the tuning fork vibrate in 1 second? It's asking how many vibrations in a unit of time. Oh, this is a little tricky. This threw a lot of people off on the homework. Okay, it's asking for vibrations per time. It's asking about some number. I know it's not saying the number of waves, so if you're confused about this, it's understandable. Okay, again, in class I'd be walking around, right, to clear things up. But it's asking for the number of vibrations in a unit of time. What does this look like to you? That was frequency. In fact, A is almost like a trick question. It's asking about frequency. What does frequency mean? It means the number of waves or the number of cycles or the number of things per second. The frequency of this tuning fork is 256 hertz. That means it vibrates 256 times every second. That's actually the answer. Okay, it's hard to see. You can't see it. It's happening so fast and so small, millimeters. You can't actually see it if you have a tuning fork and you gong it. Okay, but those two legs, they're going like this. Back and forth and 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 back and forth. 256 times a second. Okay, that's very fast vibration. So that's actually the answer for A. For B, it's asking for the period. Well, now that we know what the frequency is, or in fact, we already knew what the frequency is, that's 1 over f, so that's 1 divided by 256. You punch that into your calculator, you get a very, very small number. And that should make sense because, oh my gosh, it's doing this 256 times in 1 second. This number here represents the time for one vibration, one of these. Back and forth. It does that in 0.0039 seconds if you do the math. But that's the period. This right here, this comes from the frequency because A is really trying to discern if you understand what frequency means, but A was a little tricky. Okay, moving right along. Number 4. What's the difference between constructive and destructive? Constructive waves add up. So if this wave was going to the left, to the right, this one's going to the left, they add together. You would get a taller wave. These add together. Whereas destructive, they subtract. It's almost like canceling. Okay, let's say I have a wave like this and a wave like this. Oh my gosh, this one's going here, this one's going here. This wave is kind of going to reduce. I like to think of it like adding numbers. If I pretend this is, I don't know, +3, this looks like -1. What's +3 added to -1? Well, that's like a +2. And when I say plus, I mean it's a little bit above. Something like that. Sorry, it's not necessarily to scale, but it's a little smaller than this original because I had some canceling. I had some of the wave being subtracted. Okay, but both are what happens when waves overlap. It's a type of interference, or sometimes called superposition. It's how waves interact with one another. Number 5. In number 5, it's all about pretending. Like, let's look at A. I have this wave at the top, I have this wave at the bottom. For A and B, it's kind of tough to visualize, but pretend like you're overlapping them. Pretend like you're like cutting them out, and then you're putting them right on top. And then what would the result be? So let me see, let me get a pen, and I'm gonna go like this, because here's A, here's B. If I put these two waves on top, look what happens if I lay them on top of each other. This crest is on top of this crest. This trough is on top of this trough, right? If I lay them on top, they are on the same side. What happens when I have a crest and a crest? Is that constructive interference or is that destructive? That's constructive. I should have a taller wave. Now, what happens when I have two waves on the bottom? Is this constructive or destructive? Careful. That is also constructive. What's -1 plus -1? I say negative because they're below. That's -2. I have constructive again. This wave is all constructive interference. Here's a good diagram. The waves are adding together. This is constructive. Now for B, again, let's pretend we draw them, or we cut them out, and then we lay them right on top of each other. That's the idea when we're talking interference. If they're right on top of each other. Here I have a crest, here I have a trough. Here I have a trough, here I have a crest. Oh man, look at this. They're always opposites. Is this constructive or destructive? This is destructive. What's +1 combined with -1? That's 0. What's -1 combined with +1? Still 0. This wave would totally cancel out. If I laid them on top of each other, it's weird, but you'd have a flat line because they're canceling. Okay, so these are what I expect to draw. It's tough, but you pretend like you kind of cut them out, lay them on top of each other, and what's the result? Okay, just think, am I adding the waves? Am I adding those amplitudes? Or am I subtracting them? Next one, jumping down. Number 6, we're just about done. I kind of went ahead and did some drawing just to save ourselves a little time. Again, it's asking what happens when these waves are essentially overlapping, when they're interfering. So imagine this wave right here, it's moving to the right. This wave here is moving to the left. At some point, they're going to overlap. And I just made a rough guess of where the middle is. That's not super important. Sorry if this is actually slightly wrong, if it should be a little bit here or a little bit there. But let's imagine, again, almost like we cut those two waves out and we put them on top of each other. Here's what I have. Here's the purple wave. Okay, here's what I have in purple. And I just redrew it. I redrew it. And then I have my orange wave right here. Here's that orange. Again, I moved it here. This is them overlapping, so to speak. And let's think about if there's going to be any interference anywhere. Let me switch to red. Right here, in these first two blue squares, 1 and 2, 1 and 2, I only have the purple, the left wave. Notice there's no orange wave right here. So there's nothing to interfere with this first section. That's why here, see how I have this purple? It goes up 2. Here I have up 2 over 2. There's no interference going on here. Is there interference going on here? No, because there's only that purple wave that's present. So same thing, this green here and this green here, that's really just that original purple. Now let's think right here, now in the middle. Is there another wave that's in the same area? Yeah, now there's that orange wave. There's going to be interference right here. This is tough to visualize. It takes practice. Now, this wave is on top. It has an amplitude of +2. The orange wave has an amplitude of -4. So in the middle, here I have +2. What's +2 combined with -4? Oh, I get -2. So the result right here, right in the middle, these middle two, you have to combine these amplitudes. That's tricky. But if I have a +2 and a -4, the combination, you add those together, you get a -2. So this is the result. Some of you drew this on your paper, and that's pretty good. You understood the idea that you want to look at them when they're overlapping, but you didn't actually draw what you would see. What you would actually see, the way the string would look is right here, with them looking like this. I also redrew it right here. Okay, so this has an amplitude of +2. This right here has an amplitude of +2. This has an amplitude of -2. Okay, and I'm saying that +2 and -2 relative to this line. Okay, this is a tricky problem, number 6. Okay, just one more to go. One more to go, and we're diagramming. We can do this pretty quick now. But some of you didn't do like the full question. For A, section A, which is what I'll do here. Here's section A. We're going to just draw all the interference. Pretend like this overlaps with this, right? They're both going to be in the middle. This one's going to have an amplitude like this. This one has an amplitude like this. Will this be constructive or destructive? Constructive. I have waves on the same side, maybe something like that. Let's look at B. Is this also constructive? Yes, because I'm going to have 1, 2. They're the same amplitude. They're right on top of each other. So they're going to add up. Will it be as tall as this one? Probably not, because let's see, let's kind of pretend. Here I have 1, here I have 1, 2. 1 and 2, so here I have an I'm sorry, maybe I should say, maybe I shouldn't have done that way. I'm kind of like pretending like these are numbers. So here I have an amplitude of 2, here I have an amplitude of 1, that's a total amplitude of 3. Here I have 1 and 1, so I should have probably a total amplitude of 2. So not quite as tall, but still constructive. How about here? I have an amplitude of 1, and this is -1. When they overlap, what's the total? 0. Perfectly destructive interference. Is this destructive? Here I have maybe -1, and here I have, I don't know, maybe -1, -1. Oh, I'm sorry, this is +1. So what's -2 + 1? That's going to be a -1, maybe like that. Okay, something like that. Okay, so we have constructive, constructive, and then we have destructive and destructive. For B, B is asking to rank them from greatest height, from greatest, to the least height, to least. Let's try ranking these waves, then we're all done. Which of these waves has the tallest amplitude? The tallest amplitude? Well, A does. That's pretty straightforward. I think everyone agrees that A, it's constructive, but again, it's going to have more amplitude than B because the initial wave started with a bigger height. So A is the most. Then what has the biggest height? Well, it looks like B has the biggest height next because B has a height of 2. Okay, C has a height of 0. D has a height of -1. Okay. Well, now to be honest, for the next one, it kind of depends how you interpret this question. If you're thinking of greatest height, if you're going from positive to 0 to negative, you might say it goes A, then B, then C, then D. Because A has a positive amplitude, B has a positive, C has 0, and D kind of has a negative. If that's your reasoning, okay, I kind of understand what you mean. All right, now, to be honest, we don't really think of amplitudes in terms of plus or minus. This is more to help with like interference. Okay, some of you might, and I'll accept either one. Okay, you're not going to be quizzed or assessed based on the difference in these two. But if you said it goes A, then B, and then D, and then C, because this has 0 height and this has some height, right? It does have some height, it's just down. If that was your reasoning, well, okay, I'll take that too. All right, but this is the key. Can you draw these waves as they are interfering with each other? Okay, oh my gosh, those were the solutions. Hopefully it helps clear some things up. As always, you can email me questions. Okay, thank you for watching.